Thank you for the nice introduction and a warm welcome to everybody. And I'm quite happy to have a new example I can present here in this conference, like the last years already. I have done this. And this topic comes from engineering Mars, from the vector analysis, and I wanted to show you something what I had in mind. Um, uh, I, the summer is almost gone, and some of you and some people like to go to make a small boat trip on a lake or on a river or maybe on sea. And I have chosen this picture to introduce to you how we could explain in engineering mass as well as in fluid dynamics is a concept of the curl, or in German it's called rotation. And therefore, we have to think about how to describe a boat or in abstraction, a point in a plane. When we look here, we have the JSXGraph version of a small lake with a bit adjusted background color and some vector field. And you will see it's not a laminar fluid. And if I choose such a boat, I can drag it around over the sea. And usually we will not keep the orientation. So the boat will be rotated. I hope you can see the angle added here to the boat to describe the rotation. But what do we do in Mars? We will add a local coordinate system, which is moving with the boat. And then we describe the rotation by a rotated coordinate system. And at the end, we will everything throw away and we will have a point in a plane and added with an angle, and then we say we have 3 degrees of freedom. We have 2 coordinates and 1 rotation angle, and this is nothing new to engineers, but in discussion with my colleagues, I already have seen that for some mathematicians, this is really demanding to agree with. Um, Now I have to make a security alert. I will now handle with some mathematics and even with some programming lines. So if you feel like in an engineering math lecture or in a lecture on numerical mathematics, this may happen. So I just will tell it before, but at the end you will, or in between, you will have some nice pictures you can enjoy. When we are talking about vector fields, then from a mathematical point of view, it is a mapping from R2 to R2, or more general, we are considering the three-dimensional space, and we have component functions often denoted by an index with a coordinate axis x, y, z. And we say it should be at least one time continuous differential with respect to every variable. Okay, then at this point, the students are not always happy when we introduce a divergence, or you see here already in the headline, the nabla operator. I really like this. And then we can very compact define 2 operations like the divergence of the, this was wrong, the divergence of a vector field. This we have here, and this is defined by a scalar product of the nabla operator applied to, or a scalar product between nabla operator and the vector field. And we have the so-called curl. This is nothing else nabla times v, and it takes some time to know the definition without using a cheat sheet. We will go back to 2D. I'm started from a rigid rotation. We have a rotation axis A, and then we have a point in space, and this point is rotating with a fixed angular velocity omega around this axis A. So we can, if we like, we can try to add here such a small curve, and we will denote it with omega. And then we will describe this rotation. And unfortunately, it is a bit I hope you can see the last line. This is a description of the point over time when we will rotate around the axis A. And what happens now, you will not be very surprised when we will differentiate with respect to time, and then we make some computations. This are usually some homeworks, and we will end up with this nice expression. The derivative with respect to time of the point is nothing else omega A times x, the cross product. Then you can do some more computations, and you will end up here with this equation. And then we see, okay, this is nabla times x dot, and x dot is a vector field. So we can interpret this as the curl of x dot at time t. And then we see we have here 2 times the angular velocity omega times the vector A. And this is my model I'm using. And now I go back and I will say, okay, if I have an arbitrary vector field V, then I interpret the curl of V as a representation of 2 times omega with respect to a certain rotation axis A. And if we have this in mind, we would expect, okay, at the end, this rotational axis will change in every point in space. And now we will go back to 2D because I want to show it to you, not in 3D techniques. I will just reduce the complexity. What we know is when we go back to 2D and we will consider a 2D plane, something like this, and we have here a vector field inside, and we can imagine, okay, this is a vector field V. In this part, it is depending on 2 variables, x and y, and we have 2 components, capital V and capital Y. Then we would like to have something, the curl I already mentioned above, even in 2D. And this is quite easy to do. And at the end, if something rotates in this plane, maybe in this way, then the rotational axis will be 001. So it's a normal to the plane. Starting from that, we just have to add a 0 to our vector field. Then we have 3 components and we are happy. And now we can compute this nabla times V. And I could not skip this because I'm teaching too much engineering math. So these equations are a bit demanding. At the end, the interesting part here is missed. It's a vector A. at the end, we have this expression here. And this expression I will interpret as 2 times omega. And this is what we are looking for. And this is what we are looking for, this term. And then we see, okay, if we have the vector field as an analytical expression, we can compute the partial derivatives with respect to x and y, and we have an expression for omega as a function. And at the end, I set this expression as the angular velocity in the point xy, and I only have to handle this expression, but this we will do later on. And how does it look like? We remember we have a boat on a sea. It can turn around, and we try to reduce this to a point. So, but if you look here, then, and I have a point here going around. This is the first implementation. We have here a point. I can go along the curve. Then we have the local coordinate system in a light blue. This is a reference point. The big blue point indicates the angle we are considering. But this is a wrong example. I will start with the angular velocity. And here the angle is a measure of the angular velocity in that point. And then we see this will change. We have points where it is quite small and points where it's quite huge. And then you will see here already, I have used I can describe a curve by 2 functions, and then I have created this curve at this point, and I have not chosen a glider at the curve. I have chosen a slider to go through the positions at the curve to be able to handle the local coordinate systems. But then you see, this seems quite easy. Let's go back. I will choose a curve. Okay, this is given. And then I say I have vector field with depending on x and y. Now I have a curve. I will substitute the coordinates by the description of the curve, and then I define the angular velocity by time. The curve parameter t depends on the coordinates x and y. And I have again my expression I already described before. But this is a picture we have already seen, but I'm not only interested in phi dot, but at first we need some examples. I just try to skip them. As you have seen, this is the first example. We can compute this expression. You will see this expression looks not very nice. Much more common is this example. The vector field minus y and x as components, and if you compute the rotation of that, we will end up with equal 1. And now this seems quite easy to get the total angle over the curve parameter, just an integration. And we see in this case, the parameter will be the angle we had. So this is, we will see in the next example. Here we have this vector field. And if I start at the initial point 2, 0, and I will go around this curve, we will see at the end, one time around the circle, we will have one rotation about us. And you will see, if you look at the blue point at the end, we have done one rotation about our own axis. If you take different vector fields like that one, it's a bit different. You see it's minus x, but we have divided this by the 2 norm, the square of the 2 norm. Then we see nothing happens. And this is very strange to the students to see this or to mm, um, get an impression of it that in almost same vector field we have complete different behavior. And this was the idea why I have started to find a solution to visualize these things. Then we can make a bit different um, version where the rotation will depend on the radius. If I go to a 3 times cosine and 3 times a sine, and I choose this as a curve, then you will see, okay, the rotation and angle is a bit smaller, but the rotation in general is constant over the curve. The next is how to use all this inside a JSXGraph and to get the complete angle. But what I have done here, let's go back. Here we see a vector field and the prescribed curve. But is this what we are have in mind when we are talking about vector fields? Usually we have a vector field, we have an initial point, and then we will look at the trajectory and we'll see, okay, the trajectory will go this way, and we can go along that curve. And now I was able to add here even the rotational angle. And what I've done, I have integrated along the vector field the trajectory, and I added the angle as well. And at the end, I can add everything, and you see the old applet with all things you can set up, and you will see, okay, here are 2 new sliders coming from the numerical mathematics. And to be confident, if I choose the old example, we have it's the same behavior, but I should start at the x-axis as well. And then we see one times around the circle, we have 1 rotation about us. What I have done to manage this, at first, I have a vector field. This is a differential equation. So I entered the path to ODEs. Then I can integrate along a vector field as I like. Then I have added here the equation for the angular velocity, and I can integrate all these 3 integration at once. And the nice thing is, I do not need additional library because JSXGraph is even possible to use as a numerical library. The only thing I have to do to reinterpret everything as a vector, so I have a vector x with coordinates 1, 2, and 3, and then I will now roughly explain what I have done. At first, the x component of the vector field is stored in a variable input fx, and I have to differentiate this with respect to y. This is here in the function manipulate. This is what I talked about last year at this conference. The same thing I will do with the y component of the vector field. I will differentiate this with respect to x, and at the end I will do some string operation, and I have my function as a string phi.txt. And now I only have to build a vector function, okay, brackets, x component of the vector field, y component of the vector field, phi dot, and I will replace x by x0 and y by x1, and everything is prepared. So, and the really nice thing is we have a Runge-Kutta methods inside JSXGraph, so I could just call Runge-Kutta for the classical Runge-Kutta method, and I can integrate starting from the coordinates of my initial point and with 0 initial angle. And then I have some numerical parameters. Okay. But what I have done, This point here is not implemented as a glider. It is implemented depending on the parameter t from the slider. But what does it mean? I have to evaluate for the x and y coordinate the slider, so I need functions. But even here, we have a lot of nice helper functions. I can, this I do in several steps. Here, I just retrieve in a numerical way the data from the integration, and then I will build up splines. One spline for the x coordinates, one spline for the y coordinates, one spline for the rotational angle phi, and then I will put inside here the t vector with my curve parameter and the solution at several points. And at the end, I can create the point with two arrow functions. For the x coordinate, I will evaluate a spline with respect to x. And for the y coordinate, I will evaluate a spline with respect to y. And thus, I can create a slider, and the point is running around, and it looks like a glider. Okay, but you see here's a rotated coordinate system, and I discovered during this work the option to add transformation to objects. And this is what I have done here. I have implemented both. If I'm looking at phi dot, then I have to evaluate just the phi dot function. So this is the angular velocity at the point. Or I will consider the accumulated angle. Then I have to evaluate again a spline. This is a spline with respect to phi. And so I could add everything and put everything together. And then I have done two things. The local coordinate system here in the light blue is described by 4 points and 2 lines. And at the end, I said, okay, take these points and rotate them around the point at the curve. And this is what you see here. I take the old point and I apply the transformation I have defined one slide before. And so it is at the end a small piece of code. And now I will go back to our lake. You see here a small boat, and now this boat can run around the lake. And here you see without all local coordinate systems and transformation and Runge-Kutta methods, just running a boat around. This is what I want to explain and show to you. And thanks.